Hello everybody, you're very welcome to this episode of Programming and Algorithms. In this episode we're going to look at software testing. This week as well we're not going to do any Python at all, we're just going to focus on two particular domains without looking at any Python because it's important to understand some of the general principles. So in terms of software testing, we'll recall that it's checking if there's errors in the code and really running the code and checking if it works is one thing. Checking if it compiles is great. And trying different kinds of input to see what crashes the code. So it's really an investigative process. In terms of how this works, very often in IT companies at least, a customer asks the IT company to develop some software. The company gets some analysts or designers to design the software. They pass those designs on to developers who write the software, and the developers pass that code on to testers who test the software. It's actually a very good idea, if possible, that the person who is testing the software is not the person who wrote it. Because there's so many things, if I write software, that I'll assume that then if I'm testing it, I'll make the same kinds of assumptions. So if I've got a blind spot about something as a developer, I'll have a similar blind spot as a tester. So it's actually better to have separate testers who are computer people as well, who look at the code, and maybe even that they go back to the analyst's design documents and find out exactly what the customer wants and make sure that the developed code matches the user's requirements. So testing results in what are called bugs. If we find a flaw, a defect, a problem, an error, an incident, an anomaly, a variance, a failure, an inconsistency, a product anomaly, or a product incident. So these are various names for there's a mistake in the code, it doesn't quite do what it should be doing. So let's look at different software testing methods. And our three main testing methods are called the box approach are black box, white box, and grey box testing. So we did this before in the first semester. Black box testing means we don't look at the software at all, we just run it. So we don't care how it works at all, we just try different inputs and see what happens. So let's say I have a field called date of birth. If I put in today's date, what happens? If I put in next week's date, what happens? If I put in January the 1st, 1842 as a date of birth, what happens? So just if I put in A, B, C, D, E, F, G for a date of birth, what happens? So I just test just the user interface, the inputs and outputs, and check if the system behaves correctly without any knowledge of the input. So it's like I'm driving a car and I don't know how the engine works. The opposite is called white box testing, where I look through the code and I look at the parameters being passed to methods, and I look at the array structures of the linked list, and I look at the if statements and the else's, and look at the loops and everything. And then by examining the code, I check if the code is all working. So that is opening the hood of the car, looking at the engine, checking if there's water in the water can, and checking if there's oil in the oil and things like that, and seeing that the fan bolt is still connected on and the spark plugs are working. So that's looking at the internals of the code. So we can either black box test, which is just run the program without looking at the code, or white box, which is looking at the code. And then we can do somewhere in between, which is grey box testing. So grey box testing means looking a little bit at the internals and looking a little bit at the externals. So some interface stuff and some code stuff as well. And that can be a really effective approach, because sometimes the errors will be interfacing and sometimes the errors will be within the code itself. So a bit of grey box can be extremely effective. So that's called the box's approach to testing. In terms of the type of testing we do, there's a bunch of different types. The most basic is called unit testing, and unit testing occurs when we just look at one line of code at a time. So we look at this if statement. If, what's the condition? What's the then part? What's the else part? So we break the code down into one line at a time and one module at a time. One up is called module testing, and that's where we test the whole of the module. So what we can do in some programming languages is, if we've a program that's got a lot of modules in it, pull one module out and shove it in what's called a testing harness, which means the testing harness will pretend it's the rest of the code, and it'll feed in whatever parameters this module is supposed to take and catch any return values that the module is sending back out. and we can just test if the module works under a variety of conditions. So our testing harness then can feed in a variety of inputs into the module and make sure that the output, the return values are all correct. Subsystem testing means when we test the interface between two modules, if the value is being passed between one module and the other, is that effectively working in all cases? Are there any error conditions where one module will fail to pass a value onto a different module that's expecting it? And related to that is integration testing, where again we're testing subsystems, but we're looking at things like stress testing, where okay, the code works when one user is logged in. Now let's log in 100 users, and does the code still work? Let's log in 1,000 users, and does it work? So for example, I guess on that tickets.ie website, or any of those websites that sell tickets, when a U2 concert comes up, all of a sudden the system crashes because it hasn't devoted the company hasn't gotten enough processors available to deal with all the web requests to book tickets for U2. So stress testing is let's test it as if 1,000 people are testing it. Or volume testing is let's keep on testing it for hours and hours on end. Obviously the human being doesn't have to do that. We can create software programs that will run these jobs in batch and run them overnight and things like that. Then we have acceptance testing, where we test the whole system live with either live data or simulated data and establish if the system really works and establish if it does what it's supposed to do. So we might get the person who asked the software to be written, the customer, to come in and test the software. And if they accept that it's what they want, then acceptance testing is passed. In terms of the principle of testing, we always go back to this chap, Edsger Dijkstra. So Edsger Dijkstra, born in 1930, died in 2002, was a Dutch computer scientist who was responsible for a number of different contributions to programming languages and formal programming and things like that. He said one of my favorite phrases, he said it in a few different ways. He said testing can show the presence but never the absence of bugs. Or he said program testing can be used to show the presence of bugs but never show their absence, or later on he said never prove their absence. So if I test a program and I keep testing it and I find there are errors in it and then I fix those and I keep testing it and then I stop, it doesn't mean that I've found all the errors in the code. It just means that the program has passed all the tests I've done. There might be some weird test I forgot to think of that if I'd thought of, it would have crashed the program. But just because I've tested something 100 times does not mean I've found all the errors. It just means I've found all the errors that those tests will reveal. So testers have to be really clever in terms of thinking of a wide range of tests. Again, if I'm putting in date of birth and I put in a real date of birth, a date of birth for somebody 2,000 years in the future, a date of birth for somebody 2,000 years in the past, if I put in XXXXX, what if I put in blank? Maybe I wouldn't think to put in blank, and maybe putting in a blank date of birth would crash the whole system. What if I put in minus 1993? What happens then? So the tester must think of as wide a range of cases as possible to test so that all of the potential bugs can be found. But repeated testing never proves that there are no bugs. It just helps find them. So that is principle number one of testing. Testing shows the presence of bugs but never proves their absence. Principle two is exhaustive testing is impossible. So what I was saying there about the various tests we could do about date of birth, we could never actually test every year, every potential error that a user could type in, because they'll think of some wacky error. So it's impossible to think of every case that a user could type in. All we need to do, the best we can do is think of what are the cases that a user are most likely to do and prioritize the ones that we think are likely a user will do. And the more time it works like this. The company that's developing the software will only spend a certain amount of time developing the code. If a customer comes to a computer company and says, I need this code in 6 months, the company has to make decisions. It might say, we'll spend a month doing analysis, we'll spend 4 months developing, and then we'll spend the last month testing. After that last month of testing is over, that's it. Even if all the tests haven't been done, it's over. They have to ship the software. So we can't test everything because it's costing us money, the more testing. We're paying people to do this. So we can't exhaustively test, but what we need to be able to do is test the most likely things to occur and the most serious things. I would say as well, and this is important, if I'm writing software for a nuclear power plant or a heart-lung machine, I would test that a lot more exhaustively than I would test an e-commerce website or something like that, because the consequences for a nuclear power plant software not working are way, way more important than for an e-commerce site to the general population. So if we want a lot of testing to happen, the customer needs to pay for it. Principle number 3 is that early testing is important. So as soon as the customer tells you what they want, we need our software to do such and such thing, you develop test plans, then you develop what kinds of things need to be tested then. And as the analyst, you pass those test plans onto the testers so that they will run and see if those work. Test in development, design tests in design, test during development, and test during testing as well. Principle 4 is, and this is a curious fact, but it's always true, almost always true. If you find an error in code, look around 2 lines up and 2 lines down from that code, because there'll probably be another error near there. And it's just one of those things that defects tend to cluster together in a small area. I think it's a lot because of what people used to call car manufacturing Friday evening or Monday morning coding. On Friday evening, when you're writing code, you're more or less distracted by thinking about what I'm going to do at the weekend. So your coding is slightly off on Friday evening because you're just trying to rush through coding and your modules mightn't be as well developed as you hoped. And then the same on Monday morning. Not that you'd have a hangover, but you might be a bit tired on Monday morning, so your code is a bit ropey on Monday morning. So they used to talk about that in car manufacturing. Cars built on Monday morning or Friday evening were not as good as cars built in the middle of the week. And in the same way, if I'm having a bad afternoon or a bad morning, I'm going to produce a lot of different errors in the same little cluster. Principle 5 is the pesticide paradox. So I'm sure we know that the more you use pesticide in crops, the more the crops become resistant to it. So we can't use the same pesticide over and over again because the crops become resistant to it over time. And in the same way, if I always test dates using a blank value, letters, a number, 2,000 years before today's date, 2,000 years after today's date, if I get a new software system to test, I shouldn't use the exact same tests again on it, because if this, let's say the new system is dates of birth for kings of Egypt or something, a date of birth 2,000 years ago would make sense then. So we change our test plans on the basis of the system we're doing. Although a lot of testers do use the same testing approaches over and over again, it's not necessarily a good idea. For every new system you test, you should develop new test plans for that. Principle number 6 is that testing is context dependent. So as I said before, if it's mission critical, if it's a heart-lung machine or a nuclear power plant, we should test that way, way, way more thoroughly than if it's something like an e-commerce site. Principle 7 is, even if the code works and even if it compiles and it does everything, that doesn't mean it does what the customer asked you to do. So just because there's no errors, you need to test it in the sense of acceptance testing to test, is it what the customer asked for? Sometimes what happens in the software development process is something called concept drift. You start off with whatever the user wants, and they want a system like this. But then when you create the design documents, it shifts things a little bit, and then the developers change it a lot. By the time it gets to development, it's drifted away from precisely what the customers asked for. So you need to nail that down and try and prevent concept drift as much as possible. And that's some principles of testing. So I want to talk about a typical testing process now. And there's a few different stages in it. Normally, and it follows the software development cycle in a way, There's the planning of the tests, there's the analysis and design stage for testing, there's the implementation, executing of tests, evaluation of exit criteria and reporting, and then there's test closure activities. So in terms of planning and control, it's really to understand the goal and objectives of the customers. What do they want from the system? And what risks are they worried about that we need to test to ensure that our software does that? When we've decided that, then we have our mission of testing, or the test assignment. What's the goal of this testing? Next, to achieve that mission, we need to develop strategies and policies. A test strategy is an overall approach. System testing will be carried out by independent softwares is a strategy, whereas a policy is we might review all design documents. And testing doesn't just have to happen on code, it can happen on Word documents or design documents as well, diagrams, anything. You can test to see if the diagrams make sense. Once we've got our strategies and policies, we can create test plans. And a test plan is really to determine the scope and risks and clearly articulate the objectives of the testing. And for that, we need to understand what language we're developing it, what operating system we're developing it on, all of those kinds of issues. And implement what's needed in that case. We also need to figure out what testing resources are required, what software is required, what people are required, what hardware is needed. Will it be a separate PC or laptop being used for the testing as for the development? We need to decide what members of the team will be part of the testing team and set up and configure all the software and hardware for a test environment that might include an extensive test data suite and might include a spoof e-commerce site. So let's say we're developing something that will connect to an e-commerce site. If we're just developing the software that connects to the e-commerce site, we don't need to test it with an e-commerce site. We can create a fake site that'll simulate that for us. So, and we need to figure out scheduling in terms of our development cycle. As I said, if it's 6 months, what's going to happen in the first month? What's going to happen in the next 4 months? What's going to happen in the last month? When are we going to do the testing? How much? How many people? All the resources and activities. Also, we need to determine what we call an exit criteria. That is to say, when we say enough is enough. So how do we draw a line and say that's the testing done? And we decide that in the analysis stage of the problem, not when we get to testing. Test analysis and design thinks about more tangible aspects of testing. We've got a plan now, so let's figure out, are we going to do black box or white box testing? Let's look at priority in terms of tests. What ones should we do? Let's see what kind of data we're going to use to be testing. Do we need a large volume? There are some software testing tools that will generate fake data for you, which can be very helpful. Are there confidentiality issues and things like that? So every once in a while you hear how a software company accidentally lost data from one of their customers because the customers gave them live data. So that can be a bit of a mistake. Finally, we design the test environment setup and create the tools, set up the tools, create the environment and get it up and running. In terms of test implementation, execution, let's build those test cases. Let's set up the testware. Let's get the scripts written and the batch files written. Let's prioritize our test cases. Let's group similar tests together. And let's verify that the test environment is working correctly. In terms of executing then, let's run all the tests. So we'll create macros or test suites and we just get them running. And let's figure out what we expect in terms of results and let's look at what we actually got in terms of results. We'll run these automatically and then we'll read logs afterwards and the logs will tell us whether the system worked right or not. And then we can compare the test execution to the objectives of the development. And again, to get back to our exit criteria, decide when enough testing is done. And that's, as I said, that's using the logs. And we create a test summary report for the users or the customers. And then Our last thing is test closure activities, where we check all the deliverables have been delivered. We finalize and archive all the testware, the scripts, the infrastructure and things like that for future projects, and we evaluate how well the testing went and learn lessons about the testing cycle we undertook. So thanks very much. We'll see you on the next episode.